we now put it all together and consider a multi-step synthesis problem that will involve carbon-carbon bond formation as a key step. Okay, so the problem I want us to consider is preparing the 12-carbon ester indicated on the screen from starting materials that contain 4 carbons or less. So how do we even start thinking about this problem? Well, we start by looking at the functional groups, and the most obvious functional group is an ester. And the way we prepare esters is through acyl transfer reactions. So the obvious acyl transfer reaction to use is one between an alcohol and an acid chloride. And we can do that. That will give us a 4-carbon acid chloride reacting with an 8-carbon allylic alcohol. However, because the alcohol is 8 carbons, it will need to be formed using at least one carbon-carbon bond forming reaction. So ideally, in order to only have to do one carbon-carbon bond formation, we would like to break this molecule apart into 2 4-carbon fragments. So that brings us into what's fundamentally the retrosynthetic analysis of the 8-carbon alcohol. I now have the carbons numbered, and in order to be able to break it into 2 4-carbon fragments, we have to be able to form the carbon-carbon bond between carbon 4 and carbon 5. And the good news, it is actually good news, although it may appear to be bad news at first, is that this is a carbon-carbon double bond, not a carbon-carbon single bond. So you may think, oh no, not only do you have to form one carbon-carbon bond, I have to form 2. Well, you are technically forming 2, but they're in the same place. So the only reaction that we know about that will form a carbon-carbon double bond is aldol plus dehydration. However, the product of an aldol plus dehydration reaction is an alpha-beta unsaturated ketone, not an allylic alcohol. So depicted here, if hypothetically, instead of having an alcohol at C3, we had a ketone at C3. This is purely hypothetical at the moment. That alpha-beta unsaturated ketone can be formed through an aldol plus dehydration. Okay, so we would have the left-hand fragment containing carbons 1, 2, 3, and 4. That's a ketone fragment. And then an aldehyde fragment containing carbons 5, 6, 7, and 8. Okay, now, to move from the hypothetical to the real, is there another reaction that can convert the ketone that we would get out of this aldol plus dehydration into an alcohol? If so, we can put this other reaction in between the 2 coupling reactions. And the answer is yes, otherwise I probably wouldn't be taking us down a fruitless path. And the reaction that we need is reduction with a hydride reagent. Okay, remember in our first lesson in this unit, we had reactions that increase molecular complexity and then functional group transformations. And this is a functional group transformation, converting a ketone into an alcohol. And we said that the functional group transformations are often used to set up the key coupling reactions that increase molecular complexity. And that is precisely what happens in this problem. So the hydride reduction will go in between the aldol plus dehydration and the acyl transfer reaction. Okay, so let's look at the final synthesis in the forward direction. So reaction 1 is going to be aldol plus dehydration. And this reaction is going to require LDA as the base because it is a crossed aldol, and luckily we are fine with this because what we need is the kinetic enolate, the less substituted enolate of 2-butanone. So we're going to deprotonate that with LDA, add butyraldehyde, and then we're going to need to heat it up in order to undergo the dehydration reaction. Okay, so that all that is one reaction, happens in one pot on one day. Next, after you have this product on another day, you come into the lab and you set up the reduction reaction. Reduction of the ketone to the secondary alcohol. Now, in theory, we could do this with sodium borohydride. That was the reagent you first learned about in the context of reducing ketones to secondary alcohols. I have chosen lithium aluminum hydride in this case because the only potential complication is we want to make sure that this is completely a 1,2 reaction, a 1,2 reduction of just the carbonyl without having any competing 1,4 reduction product. That would not get us what we want. So using lithium aluminum hydride, that reduction reaction is fast and irreversible, and we know for sure it will give us just the 1,2 product. As I said, sodium borohydride would probably be okay, but you frequently actually do get a mixture of 1,2 and 1,4 reduction products with sodium borohydride unless you use some kind of co-catalyst. Okay, so we've reduced our ketone to our secondary alcohol, and now the final step is the acyl transfer reaction, where we take the alcohol, use it as a nucleophile, and add our 4-carbon acid chloride, put that together to give the ester product. And I am using pyridine as both the solvent and the base in this reaction because that can serve to remove the proton that is generated during the reaction. The OH hydrogen has to come off, and then we don't want to generate the strong acid HCl in the course of this reaction. Okay, so that's in many ways what I consider the pinnacle of this course. We have put together 3 reactions: a carbon-carbon bond forming reaction, a reduction reaction, and then an acyl transfer reaction to be able to synthesize a 12-carbon molecule out of 3 4-carbon fragments. In our remaining lesson in this unit, we will look at one more variation on this theme where we have an additional functional group to deal with.